Advanced math? Math I forgot? Math I never knew? Well, today we're going to talk about the mean squared error, MSE, in its statistical form. In a later video, we'll cover MSE for cost function. But don't worry, we're going to break it down and make it easy to understand. No tricks, no extra factors, just the true average squared error that statisticians and data scientists use to evaluate regression models. Let's talk slope. In the mean statistical error, we want to find out what's our error. But in order to figure out what our error is, we have to have an estimated guess. What's our hypothesis? Well, let's pretend we're going to 3 parks. Each park, we're going to ask people if they like chocolate ice cream. I'm going to guess that half the people want chocolate ice cream. And so that gives me my predicted slope of 0.5. Now to get my true data points, I'm going to go to Park A and ask one person, hey, do you like chocolate ice cream? That person said yes. Okay, I write it down. And then I went to the 3rd park and I find 3 people at that park and I ask all 3 of them, do you like chocolate ice cream? They said yes. And there was 5 people sitting on a bench. I asked them, do you like chocolate ice cream? They said yes. Turns out, all the people I asked just happened to like chocolate ice cream. So then you can see on the screen, we get the points 1, 1, 3, 3, and 5, 5. Now we want to find out what's the difference between the slope that I predicted and what I actually got. On the screen, you'll see the line that has f of x equals 0.5x and a table of points. On the left, we have a red line, our model, f of x equals 0.5x. On the right, we have 3 data points. You can see our columns and rows there representing the x and the y axis with the numbers 1, 3, and 5. x1 and y1 equal 1, x2 and y2 equal 3, and x3 and y3 equal 5. Our model takes an input, it multiplies it by 0.5, and outputs a prediction, which is your f of x. Our goal is to measure how wrong, on average, these predictions are compared to the actual y values. What are f of xi and yi? Let's decode the notation. F of xi is the model's prediction for the ith example. Yi is the actual label, the true value. For that same example, so when you see f parentheses xi parentheses minus yi, think predictions minus actual, the error for 1 data point. Now let's go into some examples. So our first example, compute f of xi and its squared error. From the table, we'll start with x of 1 equals 1 and y1, which also equals 1. Our model is f of x equals 0.5x. Therefore, f of xi equals 0.5 times 1, which equals 0.5. And then our y1 equals 1. So now we just put them into our formula and we compute the error. So f of x1 minus y1 equals 0.5 minus 1, which equals a negative 0.5. But we don't necessarily want to have the negative number, so let's go ahead and square it, and we get 0.25, which is a positive number. It's nice to work with, it's easy. So the squared error for the first example is 0.25. In the second example, we're going to use x2, which equals 3, and y2, which also equals 3. And that gives us the formula f of x2 minus y2. In our second example, we are talking about the 3rd park. So we asked 3 people, do they like chocolate ice cream? And they all said yes. So for this one, when we put in our formula, so f of x still equals 0.5x. So therefore, 0.5 times 3, which equals 1.5. In order to calculate our error, f of x2 minus y2 equals 1.5 minus 3, which gives us a negative 1.5. The squared error is negative 1.5 squared, which equals 2.25. 2.25. And the result for the formula is f of x2 minus y2 equals 2.25. And our third and final example, x of 3 and y3, they both equal 5. So with our formula, f of x3 equals 0.5 times 5, which gives us 0.25. And our error is 2.5 minus 5 equals negative 2.5. Now let's square it and give us a nice positive number, which is 6.25. So if f of x3 minus y3 squared, therefore our answer is f of x to the third minus y to the third squared equals 6.25. Why are we squaring these errors instead of using f of xi minus yi? There's two main reasons I like to use, and there's many more out there. Squaring makes every error positive. A prediction that's too high and one that's too low both count as mistakes. Squaring stops them from canceling out. Squaring punishes big mistakes more than small ones. An error of 1 gives us a cost of 1, but an error of 3 gives us a cost of 9. Larger errors hit much harder, so the squared error captures the size and the mistakes and keeps it all positive. Next, let's talk about this funny little symbol here. It kind of looks like an E. This symbol is called the sigma symbol. EI equals 1m, which means add this expression as I goes from 1 to m. Here's the expression. F of x I minus yi squared. So then it'll be E, or the sigma, which looks like the E, with the m on top, and then I equals 1 at the bottom. Then you'll have the formula that we've been talking about, the f of xi minus yi squared, which means add up all the squared error for every example in the dataset. For our 3 points, we found that it's 0.25, 2.25, and 6.25. And when we add them all together, we get 8.75. Now we turn that total into an average, the statistical mean squared error by definition. Now you're going to have your MSE, which is the abbreviation for mean squared error, equals 1 over m on top of the sigma, I equals 1, and then we have our formula, the f of xi minus yi squared. And this is the pure statistical MSE, the average of the squared error across all data points. Let's plug in our numbers. The sum of the squared error is 8.75. The number of examples is 3. So our m is 3 for the number of examples. Now our formula, we just plug in those numbers. So 1 over m is now 1 over 3 times 8.75, which was that total that we got. And our result is 2.92. Our MSE is 2.92. So for the data set and this line, f of x equals 0.5x. Our statistical MSE, the average squared error, is about 2.92. Let's recap what we just did. From the statistical point of view, f of xi minus yi is the error for one example. Now, f of xi minus yi squared is the squared error, always positive. Big mistakes are punished more. Then we come to the sigma with the m on top and the I equals I on the bottom, and our error formula is the total squared error over all examples. Then we come to our statistical mean error, which is the 1 over m with the sigma, the m up top, and the I equals 1 at the bottom, and our error formula. The true average squared error per example is a statistical mean squared error. For a tiny data set, that statistical MSE is about 2.92. Everything in this video lives in the world of statistics and evaluation. Where someone quotes an MSE in a paper or a model report, this is the version they mean. In the next video, we'll switch to perspectives to optimization. We'll take the same statistical MSE and show how it morphs into the cost function used by gradient descent. A very similar expression, but with different constants in front, chosen to make calculus and parameter updates cleaner. So think of this video as your statistical MSE foundation, and our next one as the MSE as a cost function for optimization. These videos will help you prepare for your AI certifications. Whether you're taking the AI Red Teamer from Hack the Box, you're taking college courses, or whatever studies you have, this video is your foundation. And if this video helped you see what mean squared error really means, hit the like, subscribe for more clear machine learning walkthroughs, and drop a comment if you want to see the optimization cost function video next. And I'd like to thank you for watching. I'll see you in the next one.